In the last few videos, we looked at the insertion sort algorithm, and we also analyzed the insertion sort algorithm to derive expressions for the running times. And we got introduced to a simple notation called the asymptotic notation or the theta notation to represent those running times. We are now going to look at a different algorithm which solves the sorting problem called selection sort. Selection sort is also a very simple sorting algorithm like insertion sort. And like insertion sort, we are going to first look at how this algorithm works, and then we are going to analyze the algorithm to derive expressions for the running times. Now we already looked at what selection sort is in brief in the very first video of this series. In talking about what an algorithm is, I discussed in that video in brief this selection sort algorithm, which is a simple algorithm that solves the sorting problem. So if you recall from there, the way we went about sorting an array A was in the following way. We first determined the minimum element in the whole array A of 1 to n, and we put the minimum element in the very first location of the output array, which in this case is A itself. So again, as we did in insertion sort, we are going to use the input array itself, and we're not going to use any extra space over and above the input array. We're going to create the output within the input array itself. So we're going to sort in place. So we know that in the sorted output, the smallest element should appear in the first position. So what we did was we picked the smallest element in the whole array and put it in the first position. What this means is if it was not already in the first position, we simply swap it with the with whatever is in the first position. Then having so let me just denote that little visually here. So in this array A, for example, the smallest element is this element 3 over here, and we're going to put 3 in the very first position. So what we'll do is we'll swap 3 with 20. So 3 will appear in the very first position, and 20 will be, let me write the whole array here. Um, so after the first iteration, after the first step, we have the smallest element at the beginning. Then in the second iteration, we find out what is the smallest element in the remaining part of the array. So this darkened portion is the sorted region, and the remaining part of the array is the unsorted portion. And in each iteration, what we are doing is we are determining the minimum element in the unsorted portion, and we are swapping that element with the first element of the unsorted portion, thus extending the sorted portion by one element and reducing the size of the unsorted portion by one element. So in the second step, for example, we're going to find out what is the minimum element in this unsorted portion. In this case, it happens to be 8. So what we'll do is we'll swap 8 with the first element of the unsorted portion, and that's 35. So instead of 35, there'll be an 8 here, and this 8 will become 35. So we have extended our sorted portion now to 2 elements, and we have reduced the unsorted portion by one element. So now our new unsorted portion starts from this element 18. We go on repeating this step. In the ith iteration, what we will do is we will find the smallest element Basically in the ith iteration, our unsorted portion begins from index I and it goes up to the end of the array, assuming that the input array has a length of n. We're going to determine the minimum element in A of I to n. Which is the unsorted portion over here. And we're going to take the minimum element and put it in A of I. So if we repeat this n minus 1 times, each time we are going to extend the length of the sorted portion by 1. And after n minus 1 iterations, our sorted portion will have a length of n minus 1 and our unsorted portion will have a length of 1. And you know, that's equivalent to saying that the whole array is sorted, because if there's only one element in the unsorted portion, that element must be the largest element in the original array. So we can stop after n minus 1 iterations. We don't have to go all the way up to n iterations, because after n minus 1 iterations, the unsorted portion has reduced to just one element, and that element can simply be incorporated into the sorted portion directly. So how do we find the minimum element in the unsorted portion? So let's assume that we are executing the ith step. We are somewhere in the middle in executing the selection sort algorithm. So we are in the ith iteration. More specifically, I'm just going to call, I'm just going to use the variable lower instead of I, just to indicate that this is the lower index of the unsorted portion. So what we need to do in the uh, in this particular iteration is we need to find the minimum element in the unsorted portion, which extends from index lower up to index n. And having determined the minimum element, we want to put it in the first location of the unsorted portion, which is A of lower. Now it's pretty easy to, you probably all know how to find the minimum element in an array. Assume that the minimum element is tentatively A lower itself, A of lower. So this is your input A, and this is your index lower, this is index n. Your unsorted portion extends from lower to n. So this part of the array is already sorted, and this is the unsorted portion. So assume that, so we're going to maintain a tentative minimum value, and we're going to scan this unsorted portion and update this tentative minimum if we find some element, some other element which is less than our tentative minimum. So let's assume that our tentative minimum value to start with is simply the value of the element here, which is A of lower. And the index of the tentative minimum is simply lower itself. What we're going to then do is we're going to scan this portion of the unsorted sequence, which spans indices lower plus 1 to n. So it starts from this index, which is lower plus 1, and it goes all the way up to index n. So we're going to scan this sequence, we're going to scan this portion sequentially, and every time we are looking at some element, we're going to check. So let's say we are examining this particular element at an index value given by this variable index. So index is the variable which is being incremented from lower plus 1 to n. Now if the value in this location happens to be less than our tentative minimum, then we are going to update our tentative minimum. We're going to say that our tentative minimum is no longer A of lower, it's now A of index, because this value happened to be lower than the minimum value that we were maintaining so far. So we update it to A of index, and the index of the tentative minimum becomes equal to whatever this value of index is at this point. So we, at the end of this scanning step, so that is once we exit out of this for loop, our tentative minimum is actually going to be the absolute minimum value in this unsorted portion. Right, you probably all know this. So um, having determined what this tentative minimum value is as well as the index at which it's present, if that index happens to be not equal to lower, so if it happens to be equal to lower, we are already done. Right? So we know that this, if the tentative minimum index happens to be equal to lower, we know that this element is already the minimum element of the unsorted portion, and so we can simply extend the sorted portion by one element here. But if it's not equal to lower, what we're going to do is we're going to swap that value with A of lower. So we're going to swap A of lower with A of whatever that tentative minimum index is. And after the swap step, we would have placed the minimum value in this location. And so we are ready to extend the sorted portion by one element. Now, what I showed here was the implementation of the ith step here. How do we find the smallest element in E of I to n? But in the uh, overall algorithm, this step is going to appear within a loop. It's going to appear within a loop where the lower or the first element of the unsorted portion is varied from 1 all the way up to n minus 1. So this whole code that we just saw is going to appear inside a loop. So that loop is going to be for lower in 1 to n minus 1. You just imagine that this this outer loop is going to be closed at the end of this step. So this is the very last line of the code. So I don't have space here, so I've depicted it here, but it actually appears after this statement. So after the ith iteration, we would have extended the length of the sorted portion to a length of I. Right after, when this loop runs for the very first time, at the end of the first iteration, the sorted portion will have a length of 1. Then when lower becomes 2 and this loop executes, at the end of that, our sorted portion will have a length of 2, and so on. So once this loop executes for the n minus first time, our sorted portion will have a length of n minus 1. And at that point we can stop, because when the unsorted portion has reduced to a length of 1, then we have practically sorted the array. So this is how selection sort works. In each step we are selecting the minimum element of the unsorted portion and putting it in the very first location of the unsorted portion so that it can be subsumed into the sorted portion till that point. Now let's try to analyze the selection sort algorithm. just as we try to analyze the insertion sort algorithm. But what you're going to see here is that it's going to be a little bit easier to analyze the selection sort algorithm because the running time of the algorithm is not going to depend on the type of input. Right? Notice that this code is going to be executed. So this blue part of the code, which is inside the for loop, this whole portion is going to be executed n minus 1 times. Right? So this whole portion is going to be executed n minus 1 times. And every time we execute this loop, we are trying to determine the minimum element in whatever remains in the unsorted portion. So the length of the unsorted portion is given by the value n minus lower, because n is the highest index, lower is the lowest index. So the number of elements in the unsorted portion is n minus lower plus 1. So the this for loop is going to be executed n minus lower plus 1 times. And then of course this particular these two lines are going to be executed depending on whether tentative minimum index is or isn't equal to lower. It's going to be executed n minus 1 times. But what you may note here is that the running time of this algorithm does not depend on the type of input. So even if the array had been sorted at the very beginning, we will still go through this exercise of determining the minimum element in the unsorted portion, placing that minimum element at the beginning of the unsorted portion, extending the sorted portion by one element, and repeating this n minus 1 times. So this is going to be done irrespective of whether the array was sorted initially, whether it was reverse sorted, whether it was partially sorted, it doesn't matter. So what I'm trying to get at here is that the worst case time is going to be equal to the average case time, which is going to be equal to the best case time. Regardless of the type of input, the expression for the running time is going to be the same. We haven't calculated what that expression is, but the expression is going to be the same because the running time does not depend on the type of input. In case of insertion sort, if you recall, there was that variable t sub j which depended on the value of a of j, because the number of times you would need to shift elements to the right in insertion sort would depend on how many elements there were that were greater than a of j. But uh, there is no such variability here, because if you want to compute the minimum element of any portion of an array, you have to necessarily scan every single element in that portion. You can't halt midway, because until you have seen every single element, you have no guarantees that the tentative minimum you are maintaining so far is really the actual minimum. So if you want to determine the minimum or the maximum element in an array, you have to necessarily scan the whole array. And this scanning portion, which is given by this for loop over here, will be the same regardless of what type of input it is. Right? And as you can see, if you try to compute an expression for the running time, this for loop is going to dominate the expression, because this is just going to take a constant amount of time evaluating this if condition, and if the condition happens to be true, swapping two elements of the array. This is going to be some constant. Okay, if the expression evaluates to false, it's going to be one constant. If it evaluates to true, it's going to be another constant, because you need to do this extra swap operation there. But in general, it's going to be either C1 or C2, you can say, depending on whether the if condition evaluates to true or false. This line is also going to take a constant amount of time. Let me call it C3. And then this for loop is going to take time that is proportional to n minus lower plus 1, because you have to scan all the elements in this unsorted portion. And the number of elements in the unsorted portion is n minus lower plus 1. And assuming that examining the value of each element takes constant amount of time, and updation also takes constant amount of time if that element happens to be lower than the tentative minimum. The complexity of this, the running time of this for loop is going to be proportional to the length of the unsorted portion. So it's going to be k multiplied by some constant k multiplied by n minus lower plus 1. So the expression for the running time therefore will be, okay, so I need to add another constant here, C4, because we're going to increment this variable lower from 1 to n minus 1. So the expression for the running time will be C4 plus C3 plus C1 or C2. And uh, obviously it's hard to exactly determine the expression if you don't know how many times C1 is going to execute and how many times C2 is going to execute. But let's overestimate the running time. Let's say that in the worst case, uh, C2 could execute all the time, but it doesn't matter, because as you'll see, whether we take it as C1 or C2 or some value between C1 and C2, the contribution of this portion of the code and this portion of the code is going to be insignificant compared to the contribution of this for loop. So I can say that T of n will be C4 plus C3 plus, you can say, C1 or C2 depending on which constant you want to choose, but some constant multiplied by n minus 1 plus the summation of k times n minus lower plus 1, where lower varies from 1 to n minus 1. So if we write this again, T of n will be some constant multiplied by n minus 1 plus k multiplied by the summation of this expression. The lower varies from 1 to n minus 1. So when lower is equal to 1, let's just focus on this expression. When lower is equal to 1, that is in the first iteration, you are scanning every single element of the array. So the time that you will take to determine the minimum element will be proportional to n minus lower plus 1, which is equal to n, because lower is equal to 1. So the time will be, I've taken k out, so I won't say k times n, I'll just say n. When lower is equal to 2, n minus 2 plus 1 is going to be n minus 1. When lower is equal to 3, n minus lower plus 1 is going to be equal to n minus 2, and so on. And finally, when lower is equal to n minus 1, so n minus 1 is going to be 1, and 1 plus 1 is 2. Now I can write this series as the summation of the first n terms minus 1, and the summation of the first n terms is n plus 1 by 2. And so the you can see that the contribution of the second part of this expression is going to be much more than the contribution of this first part, because the first part is uh, proportional to n minus 1 or n, whereas the second part has an n squared term. So we don't have to do we don't have to work out the details here. We can simply say that t of n is going to be theta of n squared. Right? We are going to drop the lower order terms, and we are going to ignore all constant coefficients, and we can simply write t of n as theta of n squared. And once again, it doesn't matter whether this t of n is worst case, average case, or best case, because the running time here does not depend on the type of input. So t of n is theta of n squared, all the three types of running times. So compared to insertion sort, selection sort runs in the same worst case um, running time, which is theta of n squared. The average case is also the same, because the average case for insertion sort was also theta of n squared. Now for the best case, um, here we've seen that um, the best case running time is theta of n squared for selection sort, but for insertion sort it was theta of n. Now strictly speaking, we can optimize our selection sort algorithm so that it runs in theta of n best case time. And the way to do that is by first checking whether the array is already sorted or not before we execute this loop. If the array is already sorted, we simply terminate the algorithm. And if it's not already sorted, then we execute this code that we've written here. And the reason for doing that is that if the array is already sorted, how do we check whether an array is already sorted? Well, we just check that we just scan from left to right and ascertain that we are seeing a non-decreasing sequence or an increasing sequence as we scan from left to right. That can be done in time theta of n, right? Because it's going to be proportional. It's going to be time taken will be some constant multiplied by n, which is theta of n. So determining whether an array is already sorted or not takes time theta of n. Now, if we want a good best case time for selection sort, simply checking whether the array is already sorted or not is going to achieve that best case time, because once we determine that the array is already sorted, we can terminate the algorithm there itself. And if the array is not sorted, then we end up with this particular running time. Now, because the best case time is the minimum time over all inputs of size n, it is sufficient for the best case to be theta of n. We just need one input of size n on which the algorithm runs in time theta of n. And that one input is the case when the array is already sorted, assuming that we modify the selection sort code to handle the special case where the array is already sorted. So I'm going to say if the array is already sorted, return, else I'm going to execute this loop. And in general, you can do this for any sorting algorithm. You can write a program to implement that sorting algorithm, which will always run in best case time theta of n. because all we need to do is check that the array is already sorted in the beginning, handle that particular special case, and for all other cases other than this special case, you actually run the code for the algorithm, the proper code for the algorithm, and the full code there is going to run in best case time theta of n. So any sorting algorithm can be rewritten to run in best case time theta of n. So in that sense, the complexity of selection sort is not very different from the complexity of insertion sort. In fact, in the theta notation, it's exactly the same. Worst case time theta of n square, average case time theta of n square, best case time theta of n.